Welcome to this explainer, where today we're totally deconstructing the fundamental mechanics of light. We're going to forget about the macro level behavior of optics for a bit, and we're diving deep into the invisible microscopic gears of wave propagation. We're looking at a conceptual framework that absolutely permanently revolutionized physics as we know it.
Okay, so it starts with what seems like a ridiculously simple question. How does a wave actually move forward? When we think about wave mechanics, our gut intuition usually makes us picture a single, solid entity just kind of pushing its way through space. But to really grasp how light travels, we have to completely flip our perspective. We literally need to abandon that macro level intuition and zoom way, way in to see the exact micromechanics at play here. Section 1. The radical tiny waves concept. Enter Christian Huygens, who was a seriously brilliant 17th century physicist. He looked at this whole problem of wave propagation and proposed a solution that was just completely outside the box for his era. Formulated around 1678 and later published in his massive 1690 treatise on light, he completely reimagined optics. He argued that every single point on a wavefront doesn't just, passively drift forward. Instead, each point acts as a tiny independent source of brand new waves. And that brings us to the formal definition of what we now know as Huygens' principle. It states that every point of a wavefront may be considered the source of secondary wavelets that spread out in all directions with a speed equal to the speed of propagation of the waves. So the absolute game changer here is that these tiny secondary waves, these wavelets, are constantly being generated, and they combine to literally build the next wavefront. It's like the wave is perpetually rebuilding itself from scratch as it travels. Take a look at the original wavefront here, represented by that solid, curved line. If you focus on the pink dots labeled A and B, you can see how each one of those specific points acts as a brand new source. They're generating those smaller semicircles, the secondary wavelets, which are expanding outward. And here's the trick. When a line is drawn perfectly tangent to the outer edges of all those new wavelets, boom, we get the dashed line. That's the new wavefront, labeled A' and B'. Every single point expands outward to systematically push the entire wave forward. Now, what's really wild is how the geometry of these secondary wavelets universally preserves the overall shape of the wave, whether we're talking about planar or spherical propagation. On the left side, you've got distinct points along a flat plane wavefront acting as wavelet sources, and their combined outer edge just naturally forms the next perfectly flat wavefront. Over on the right, points on a spherical curve generate circular wavelets that combine to form a larger, wider curve. So Huygens' principle consistently and accurately maps out the exact shape of the propagating wave, no matter what its original geometry was. Moving on to Section 2, Solving the Reflection Puzzle. Let's actually apply this wavelet framework step by step to a hard boundary, like a mirror. When a light wave comes in at an angle, the entire wavefront doesn't hit the glass all at exactly the same time. First, different parts of the wavefront reach the mirror at different times. Second, as each specific point makes contact, that exact point on the mirror suddenly becomes a new source of secondary wavelets bouncing back. Because one side of the wave hit first, its wavelets actually have more time to expand outward than the side that hits a split second later. It's this sequential timing difference that perfectly constructs the new reflected wave in step 3. And the beauty of this is that it means we don't just have to rely on memorizing the law of reflection anymore. We can structurally prove it. By treating the mirror as this series of tiny sequential wave generators, Huygens' principle elegantly and just entirely naturally proves geometrically why the angle of incidence exactly equals the angle of reflection. The physical geometry of these expanding wavelets literally leaves no other mathematical possibility. It's practically foolproof. All right, Section 3, Refraction and Bending Light. So, what happens when a wave enters a denser medium, like going from air into water? Well, the physics alter dramatically in 3 really key ways. First off, the overall speed of the light wave decreases. Second, because it's approaching at an angle, the specific part of the wavefront that enters the denser medium first obviously slows down first, while the rest of the wave is still cruising along at full speed. Finally, this uneven, localized speed change causes the entire wavefront to pivot and rotate, which bends the light ray toward the normal line. If you focus on the incident wavefront here, that light blue line connecting points B and A, you can really see this in action. Because point A enters the denser medium first, the secondary wavelet generated at point A travels slower, creating a much smaller circle. Meanwhile, point B is still up in the faster medium, just racing forward to point B prime. By the time B finally reaches the boundary, A has only expanded a tiny bit to A prime. Connecting A prime and B prime shows us that the new wavefront has definitively rotated.
The bottom of the incident wavefront slowing down first literally forces the wave to perfectly pivot. It translates Snell's law into pure visual geometry. And the math behind this translation is beautifully straightforward. The speed of light changes from one medium to another perfectly according to the equation v equals c over n, where v is the speed of light in our new medium, c is the speed of light in a vacuum, and n is the refractive index, which is just a measure of how optically dense the material is. This change in wave speed, dictated entirely by that refractive index, is the exact mathematical trigger that changes the wavefront's orientation and produces this geometric refraction. Which brings us to section 4, the Fresnel plot twist. Science is this massive iterative process. While Huygens brilliantly solved reflection and refraction with his wavelets, his original theory actually had a pretty critical gap in it for over a century. It couldn't fully explain diffraction, the way light bends around sharp edges or spreads out through tiny slits. For exactly 130 years, from 1690 all the way to 1818, this was a huge mystery. That is, until Augustin John Fresnel stepped in to extend Huygens' idea. Fresnel added this crucial concept of interaction. He realized that these secondary wavelets don't just expand in total isolation. They actually crash into each other, overlapping and interfering. And that perfectly explained the complex, oscillating patterns we see in diffraction. Today, the Huygens-Fresnel principle perfectly captures the combined might of both of these thinkers. Primary sources generate secondary sources, mapping out planar and spherical wavefronts, sure. But now we have the added, absolutely critical understanding that all these overlapping arcs interact and interfere with one another as they move. This 130-year collaborative evolution gave us a framework that is still, without a doubt, one of the absolute cornerstones of modern wave optics. I really hope this explainer fundamentally changes how you view the light around you. Next time you're analyzing an optical system, whether you're calculating refractive indices or just checking out diffraction patterns, you'll know that billions of tiny secondary wavelets are constantly generating, expanding, and interfering to map out that path. But it also leaves us with a pretty profound thought to ponder. If a conceptual 17th century idea about tiny wavelets can still define modern physics today, what other invisible mechanics of the universe are out there, just waiting for someone to observe them from a radical new perspective?